Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. Measuring current? Simple, huh? Just grab your DVM, plunk it in series with what you want to measure, and, well, there you have it. Well, yes and no. For many applications, this will work just fine. But before you believe that reading, you need to be aware of how the innards of that DVM do what they do. This might affect whether you do it this way or pursue a different method. Back when I was working for a medical company sporting battery-operated devices, I discovered that this simple method of measuring current actually can cause the measurements to be less than accurate. In fact, it led to some totally erroneous results at the end of several days of testing. Reconfigure, retest. Now I had some results that actually held water, so to speak. So what's happening here? How do I get more accurate measurements? Well, you have to be aware of what's going on inside the current measurement device. First, let's see how they measured current in the deep, dark past of the mechanical analog meters. And don't forget to subscribe and click on like if this video is helpful to you. In eons past, in the era of the old analog meters, these were all current operated. They had a stationary permanent magnet with an armature that was made out of a coil of wire. And when current flowed through this armature, it caused a magnetic field to occur, which worked with the magnet to move the armature against this internal spring, and thus the needle would go up and down. The more current there was in this armature, the stronger the magnetic field, the further that needle would move. The smaller the level of current you're trying to measure, the more windings you would need on this armature in order to get the magnetic field that you needed to move that needle. The more windings you had on your armature, the higher the resistance of the armature. In other words, the resistance, the internal resistance of this mechanical meter would go up the lower the current that you're trying to measure. Now, because extremely very fine wire must be used to create the coil or armature of the meter, higher current meters usually used a shunt resistor in parallel with the otherwise low current meter movement. This shunt resistor actually carried the majority of the current that flows through the meter, and the meter movement itself just sips some of that current to make the meter move. I have here my 50 microamp meter movement, and I measured its internal resistance at 2,000 ohms. And then I hooked it up to my VNA, and I determined not only does this have 2,000 ohms of internal resistance, but it also has 10 millihenries of inductance at 200 kilohertz. Now, when you insert a meter like this into your circuit, you're inserting this 2,000 ohm resistance between the power source and the circuit. As such, at DC and 50 microamps of current, the meter movement will drop 0.1 volts. So our 10 volt supply has become 9.9 volts. And this is possible that it could affect your steady state measurements, even the operation of the circuit that you're connected to. Additionally, the 2,000 ohms softens the power supply. Well, what does that mean? It means that when the current draw from your circuit changes, so does the voltage on the power supply rail. Second of all, when you are inserting this kind of a meter in, remember I said you got a coil of wire, you're also inserting an inductor between the power source and the circuit. Inductors oppose changes in current. So we're talking about something with a frequency aspect to it. You know, if the target circuit has quick current transitions, such as, let's say, transmitting data that happens now and then goes away a few milliseconds later, the voltage drop across the meter movement can get even worse at that moment that the change occurs. and your circuit could become current starved. Thirdly, you're inserting an electromechanical magnetic device between the power source and your circuit. Now, if you were to take a voltmeter and connect it across that 50 microamp meter movement, and then sit there and waggle the meter movement to make the needle waggle back and forth, you would see that it is generating voltage. So every time that needle moves, there is this aspect of a coil passing through magnetic field and generating voltage. And you'll actually get a chance to see that a little bit later in the demonstration, because you'll actually see the trace on the oscilloscope do one of these things as the needle finds its new place. Now, I've created an example circuit that demonstrates what happens when I insert this analog meter between the power supply and the circuit. In the idle state, this circuit draws around 25 microamps. Now, I've included a transistor that turns on periodically to draw an additional 15 microamps for 5 microseconds. And during this period, the total draw of the circuit is around 40 microamps. I did this to simulate a circuit that might sit idle for a time and then transmit data by some means periodically, which causes it to draw more current for a brief period of time. Now let's go see what happens when we put this meter in series with this circuit. All right, I have this little circuit set up here. It draws about 25 microamps of current normally without any pulse turned on. And then I have a pulse generator set up here that turns on the little transistor down here so that it draws about 40 microamps of current for about 5 microseconds. And so we're going to see the effects of putting a series ammeter in place using the old analog meter here. Now right now there is no ammeter in series. This bottom trace is the pulse that will initiate additional current. The top one is what the power supply looks like right now, nice and clean. And when I turn on the pulse, we're now doing additional current every time you see the pulse, and you can see how nice and clean that looks. All right, so let's take a look and see what the effects of putting the old analog meter in to the circuit is. All right, here we have the analog meter in the circuit. We can see we're running about 25 microamps, which is exactly what I was planning on. And now let's turn on the pulse and see what happens to our power supply feeding our circuit. Whoa, that doesn't look so good. So you can see inserting an analog meter like this can make a huge difference in the kind of power that your circuit sees. So I've stuck some cursors on here now. Take a look at the differences here. We're at 580 millivolts to the top up here. And notice what the bottom one is. Minus 1.42 volts down here at the bottom. All right, now, remember I said that you could see the needle waggle? Well, just watch as I turn it on and off, and watch that top trace. See that waggle that you just saw in the trace is because the needle is finding its new location. Okay, so that's a lot more catastrophic than you probably thought. But you say, I'm not going to use an ancient meter like that, so what's the difference? Why do I care? I'm going to use my handy dandy DVM and I won't have any of those problems because it's this new modern thing. Well, you know, that's exactly what I was using to measure current when I got that bogus data. Now, let's see why. How do you suppose a DVM measures current? Well, it's pretty straightforward. They place a known precision resistor in series with the current that you're trying to measure. They monitor the voltage across that resistor, and doing a little math in the microcontroller, they come up with the current, because it's just a matter of Ohm's law. You have the voltage across the resistor divided by the known value gives you the current. And they already know what the resistor is. They just measured the voltage across the resistor, so they know what that is. But the internal works of the DVM has limited range that it can measure that voltage. So it needs to have the value of R change to have this voltage stay within bounds. Now, some DVMs have individual ranges that you choose. But if you use auto ranging, the meter will change the series resistance value at will, and this may occur without you having a clue that it's happening. Thus, your measurement environment changes each time it does this. Now, most auto-ranging DVMs will allow you to lock the meter in a particular range. This prevents your meter from changing the measurement environment during a measurement. You can look for a range or manual/auto button on your DVM. Now, as with the old analog meters, the lower the current you're trying to read, the greater this series resistance is going to be in order to maintain a voltage drop across the meter that the guts of the meter can reliably measure. My old Micronta DVM has an internal resistance of 100.7 k ohms on its lowest current measurement range, the 4 microamp range. Now let's see how well the Micronta meter does in making the measurement of this circuit that I set up. Okay, so this is the Micronta on its lowest range. It's telling me I have 27.24 microamps. Let's see what the power looks like getting to my circuit. Well, you know, the cursors that you see there, the two lines, are the ones from the meters. So yes, it's better, but still rather significant impact. Now here's an interesting thing. I'm going to manually change the range that we're reading on the meter. So on this particular meter, I press the manual button, and then I can press the up to go to a lower range. So now I just went up by a factor of 10. And look how much improved that is. Now, let's go back down here. We'll go up by another factor of 10. And see how much improved that is. And that all has to do with how much resistance and the like that the meter puts into the mix. Okay, so what can we do to achieve control over this measurement environment? Let's see what we can do. So what's the solution? In every case, we have to remember that the DVM is averaging the actual current being drawn. If there are current spikes or oscillations, you will never see them using a DVM or the old analog meter. In many cases, these issues may be inconsequential and you don't mind the averaging. However, there are those times when we simply have to know what is really going on. The solution begins with procuring a non-inductive resistor of known value and then placing that in series between the power source and your circuit. You gotta know the value of the resistance. So whatever resistance that you set up and establish, make sure that you measure that resistance so you know the real resistance of it, not just what the nominal values are. Now you can build one out of a number of non-inductive resistors in parallel or series to achieve both the power dissipation and the values you require. You say, well, how do I select a value? Well, there are two criterion that are often at odds with one another. The first is you look to see what the largest value you can get away with without affecting the actual operation of the circuit you're trying to test. The second one is you look to see what is the smallest value you can get away with for the anticipated current to be measured and still lay within the confines of the abilities of the voltage measurement devices we have at our disposal. And then you choose a value somewhere between those two and put it in series with your power supply to your circuit. Now your goal is to control your measurement environment in such a way that it doesn't affect the measurement that you're making while still being able to get a reliable measurement. Now once we have our non-inductive resistor built and placed in series with our circuit, we now use some sort of measurement device to measure the voltage across the resistor. Be aware that you might be measuring down into the millivolt range. Now pay attention to this. Whatever measurement device you use to measure the voltage across this resistor, it has its own input resistance, and this is placed in parallel with the resistance of your current sense resistor, changing the value. But if your current sense resistor is sufficiently low in value, and the measurement device is sufficiently high in its input and resistance, then the change is going to be inconsequential. Now, if you're fine with an average reading, then your DVM is quite sufficient if it has the capability to read the anticipated voltage across the resistor. If, on the other hand, you're interested in the spikes in current transitions and the like, the answer would be to monitor this voltage using an oscilloscope, but be careful. The return side of most oscilloscopes is ground, not floating like your DVM. You must be aware that connecting the return side of your scope to either end of that resistor is going to connect that end of the resistor to ground. If your power source is ground referenced, then a lot of unhappiness will happen, loud spitting, sparking, unpleasantries. You must either lift the ground of the power source or lift the ground of the scope. But there's a thought. What if I put the current sense resistor in series with the power supply return? Then I can connect my scope return to the power supply return, all ground referenced, all happiness, connect the probe to the other end of the resistor, and everything is wonderful. Well, most circuits don't do very well with a soft ground because all signals and currents of the circuit are referenced to this ground. And I've tried this myself, and I can tell you from personal experience that the results may not quite be what you might like or expect in many cases. So this is how you can get around the problem and get control over your measurement environment and know that you're getting a good current measurement. Well, now you're prepared to measure current and know that you're getting measurements that you can believe. I hope this has been helpful to you. If it has, be sure to click on like and subscribe to this channel. Thank you so much for watching. Until next time, Toodle-Oots.